you hear me? Is this on? All right. Hi, I'm back. Good to see you again. So in this talk, we're going to be going a little bit deeper into Pluton, into some of the silicon features of the 3620 and what we expect to see in other Azure Sphere chips, and what basically makes them some of the interesting features that makes them unique. This is not a 50-minute or 45-minute talk, so there's plenty of time for discussion at the end if you'd like to chat about it. So as I mentioned earlier, there's a brief recap. We were talking about microcontrollers, these crossover, we call crossover MCUs as part of the Azure Sphere platform, and we're really focused on making sure that these 7 properties are present in the platform. So today, for this deep dive, we're really going to be focusing on hardware to trust and how that hardware to trust is embedded on die in an Azure Sphere platform. So what does it mean to have a secure hardware to trust? Okay, this is the summary slide we have, I apologize, with connection, security, and crossover MCU. So what do you get for Pluton? Well, one thing that I want to point out when we think about Pluton, we have a lot of discussion around this, is that Microsoft really thinks about a distinction in a hardware to trust about you'll often see in MCU you have crypto accelerators. There's an AES engine, there are ECC or RSA engines available to you. There may even be some key storage, and that's the hardware to trust. We think of Pluton, and then the question is, well, your application, especially if you're in an RTOS, is going to be using those crypto engines to accelerate common tasks. When we think about Pluton, Pluton is really dedicated for the use of the operating system, and if there is a need for an application to accelerate, let's say, cryptographic tests independently, we actually expect there to be separate crypto engines on die that are available to those applications. The reason partially is just security. Trying to think about multiplexing critical security needs in a Pluton from the operating system with a customer app that may or may not be compromised is pretty difficult to think about and reason about without putting the platform at risk. We're also just talking about just having device certificates not sufficient. I had somebody come up to me after the last talk and ask about, he said he worked on Blu-ray and asked about certificates and how certificates reside in the device. We don't have certificates in the trusted computing base. We don't parse certificates on a matter of principle inside our trusted computing base. Parsing a certificate in your trusted computing base we generally view as too complicated. So we're really actually inside the trusted computing base, we're just focused on keys and key pairs. And we can talk a little about in Q&A or even at lunch about key provisioning, how we deal with key provisioning, and why this is different than using a certificate as a proxy. And the other thing that we're going to talk about and cover is how that root of trust is provisioned really matters. How is it managed? How is it managed in the factory? How is it managed in your supply chain? What's your threat model from the point where the hardware root of trust is produced? Ryan mentioned an on-die root of trust versus an off-die root of trust. There's a significant improvement in security from having a hardware root of trust that's actually on die and isn't connected on a board. If you're looking at, let's say, a threat model with physical attacks. So Pluton really guarantees authenticity of your software. We're using ECDSA for secure boot. We're guaranteeing that the software is genuine. Unlike other platforms, there's no what we call third-party signing. So a common strategy is to have different manufacturers or different producers of different software components that coalesce to put together an operating system, each sign their own component, and those signatures are verified independently with different keys or different chains of trust. Microsoft signs everything. We sign every piece of software on the device. If it isn't signed by Microsoft, it doesn't run. And we protect the signing keys, basically the same infrastructure that we use to protect the Windows signing keys. So with the viewpoint that your signing infrastructure is only as strong as your weakest infrastructure in all the different software that's signed. Also protects against downgrade attacks. I mentioned this earlier in the first talk. This is a classic attack that we've seen in other platforms where you have a known vulnerability in a piece of signed software. And so the easiest thing to do is you just trick the device into downgrading to that piece of software, and then you launch an attack with a 0-day or some other well-known exploit. Once you have a CVE for a version of your software that's out there and it's well understood, then a signed valid piece of software is now an attack vector. And so we're actually able to blow fuses inside of Pluton that can guarantee only certain versions of software will run, and any version of software prior to that can never be run again. That's a very strong step to take, because once you blow fuses, it's irrevocable. And so we really generally only do that if there's the most egregious exploits that we're worried about somebody rolling back to and exploiting. It guarantees the authenticity of your device. So when each Azure Sphere chip is birthed at the packaging facility, Microsoft actually collects the public ECC attestation key at the silicon manufacturer, which means we know about every single device before it leaves the factory. So that means we can guarantee that when a device comes online and goes through an attestation process, that we've already heard about this chip. In fact, we've had instances early on when we developed the product where there was a hiccup in the manufacturing flow and we actually didn't hear about some keys. And then we had a customer calling us and saying, why won't any of our devices connect to the internet? And we said, oh, well, that worked. And so we actually had to make sure that we're registering all those public keys. So knowing about the birth of every single chip means that we're not worried about counterfeit chips. We're not worried about chips that are appearing later in the supply chain and then having to register with us. What actually ends up happening is that the chips are registered at the silicon manufacturer, and then Microsoft knows about them. They're called unclaimed chips. And then when you have a manufacturer that purchases that chip through the supply chain, they do something called a claim. And a claim is something that proves they have ownership of the device and then moves that device effectively into their ownership in their cloud services. Also reduces supply chain risk. You know, one thing you're reading about, I think it was a set of phones that were compromised in a warehouse. They were rooted, and then when they were delivered, there was malware on those chips on the phones, so when they were turned on, they were always recording. When we think about supply chain risk, we're not thinking about delivery mechanisms, but we're thinking about ensuring that software always has to be signed and that there's no escape hatch for those chips that generally turns off signing from one of those chips. So you can't load unsigned or unknown software onto the device and put your supply chain at risk. It does accelerate cryptographic tasks. It does internally have AES and ECC engines, but like I mentioned earlier, those are used exclusively for Microsoft's own usage to make sure that those operations don't get in the way. It also has a bunch of other operations you might expect, like fast hashing. Pluton also protects against what we call low entropy attacks. So anybody familiar, it has an on-die random number generator that does collect entropy from the environment, and it measures its own entropy. And if it detects that the entropy it's using to generate numbers falls outside of some sort of constraints, then it actually shuts itself off. So someone attempts to, say, cool the chip to reduce entropy so that it can attempt to attack some of the cryptographic protocols, it simply stops producing random numbers. And so that's built in on die as well. And that's part of the key when we talked about supply chain risk as well. Pluton actually generates its own keys. So often what you'll see in an MCU is that you'll have an HSM on a factory floor, and you generate public-private key pairs, and the private key actually travels over a wire and gets put into the chip. That means the private key is exposed. With Pluton, it generates its ECC keys in silicon using this entropy-based random number generator, and the private key is never exposed outside of the Pluton fabric. Even the most trusted software, there's a mention, Ryan described the Pluton runtime, never has access to those keys. So there's a higher level of security for the private key. The really only way to get access to the private key is to decap the chip and then use an electron microscope and extract them. And we've just decided that that's outside of our threat model. So that's something that is a threat vector that is available to someone, but in the process, it'll destroy the chip. So in summary, and just for some of the more details you might be interested, we have a hardware to trust, accelerates common cryptographic tasks, generates its own public-private key pairs, implements secure boot via ECDSA, its own dedicated memory and core that reads a set of side channel attacks, and a true random generator that defends against low entropy attacks, and measure boot and remote attestation. It uses a digest accumulator register and a nonce register. And the reason why this is important, and Ryan hinted at this as well in his talk, is that even if after boot the Pluton runtime software were compromised, it's impossible to forge an attestation value because this digest register always accumulates and goes up. If the Pluton runtime is attacked, you're not going to be able to send a forged value up to the cloud. This register only gets reset when the entire chip is reset. And we'll get in a little bit later in the talk about why that's important and how we use attestation to generate basically a trusted token across our ecosystem. So the Cortex-A, what do you think about? Well, the Cortex-A, and this when we talk about MCUs, everyone says, well, Cortex-A isn't part of MCU. That's why we talk about the term crossover MCU, because we think of having a Cortex-A is so important if you're going to connect to the internet. You can't just be relying on Cortex-Ms. Think about security, portability, and extensibility. On security, we think about isolation. Cortex-A has an MMU, so you get process-based isolation. We leverage this as part of the application sandbox that we've gone into earlier today to protect applications and services. It's a specialized operating system. We don't have a shell. We don't have user accounts. We don't have passwords. We don't have usernames. All of those pieces have been stripped out. And we use the client and server certificate authentication for cloud communication, so we can prove that we're talking to Azure, and Azure can actually prove that it's talking to an Azure Sphere chip. And finally, we have this capability mechanism that authorizes access to resources that's secured by Pluton. And I'll get a little more detail about what the silicon provides to protect against attacks in this space as well. Finally, it's interesting. We had a discussion last night around MPU versus MMU. Quite frankly, having an operating system with an abstraction that programs the MMU and gets it right once is a huge win. If you're used to programming M cores and programming your MPU every time you roll out a new application or a new product, is quite frankly can be error prone. So we're a big believer in OS abstractions and being able to leverage things like MMU to protect and make it easier to get to market with your application, your products. And finally, we're convinced that being able to have source portability and leverage all these open source libraries in the open source community is key to the success of Azure Sphere. So this is really focused on, we do the heavy lifting, and then someone who's developing a device like an appliance just has to focus on the actual applications themselves to bring their device to market. And it's interesting, we think about software update, and we talked earlier about software update closing the loop for bugs, but I really think software update is also the way that you deliver new customer experiences. It's the way you don't have to wait an additional product cycle, which typically happens with a fire and forget MCU, to bring new features to market, to light up new experiences, and hopefully if a customer finds them useful, to make additional money. Another reason why we really have this A7 is for headroom for the future. We really think that having machine learning, machine translation, and vision is going to be the future of a lot of these products. Making sure that Cortex-A, I think, is part of the requirement to make sure they have headroom to deliver these new experiences in the future as you develop them. So, mention the word firewall here. It's a little bit of a misnomer. When we talk about firewalls internally, we really talk about something called a core mapper. So we implement all across our silicon the principle of least privilege. It's always deny by default. This isn't always true in silicon architectures. This means when Pluton first comes up, all the access controls are just basically turned off. The other cores don't have access to any resources in the system, and we have to open access to different resources like RAM and different peripherals. So this principle of least privilege applies to every resource in the system: RAM, networks, flash, and peripherals. If you want to map in the 3620 is interesting because the peripherals can be mapped to multiple cores. You can map an ADC block to an M core or to an A core, and then the core mapper basically guarantees that once it's mapped to that core, if an application is compromised in another part of the system, it's impossible for the attacker to gain access to a peripheral that hasn't been mapped to it. And so this is, again, part of our efforts to take advantage of these multiple cores in the system to provide physical isolation between different processes and encourage an architecture that doesn't mash together connectivity and functionality. The classic example is the stoplight. If you have a connected stoplight, you don't want the same core and software that's connected to the internet and sending signals to also be the thing that's actually flicking, let's say, GPIO pins and turning the lights on and off. You want some separation there, and having an A core plus an M core really lets you have, in addition to software separation, physical isolation. I think that's a big win. So this is what I mentioned, that this really prevents compromised peripherals or compromised applications. It limits their ability to get access to other resources in the system that have not been granted at boot. So when I talk about at boot, this is a feature that's a bit unusual. We talk about these features being sticky. So we think about sticky bits throughout the system. Once you have a system configuration that you're happy with at boot, we basically have write once registers. And when you write those registers, it locks the configuration in place. Again, this is all about once you have a compromise in a certain level of the system, can an attacker then remap peripherals or try to gain access to deeper areas of the, or more trusted areas of the software. These sticky bits reset whenever the chips reset. But as an example, once you flip the sticky bit on the core mapper, then even if an attacker compromises the software that can program the core mapper, it can't remap peripherals to other cores. It's locked. You'd have to actually reset the entire chip, which then resets the secure boot process and gives you a fresh set of software. So in the M core, as we talked earlier, is focused on real-time computation. This is your typical MCU. It's focused on, say, deterministic execution or tight timing and access to peripherals. The M core we view as bring your own. We expect the silicon manufacturers to be delivering BSPs, delivering source for bare metal drivers to make sure you have high performance. You're not stuck just reading data sheets. But if you have existing solutions, existing RTOSs that you want to use, just bring those on and put them on the M core. And because of all these isolation boundaries that we've built, we're quite happy for you to bring your solutions there. And a lot of companies have really large investments in the MCU space, and they want to be able to reuse those investments. So we're interested in allowing them to do that. And so this means, like I mentioned, they're free to run any Cortex-M runtime they want. And that works, I think, as of today. So when you download it, if you want to load your own RTOS, we've had a bunch of different reports of people experimenting with different RTOSs like ThreadX and Zephyr and FreeRTOS. You can do that. So we have a bunch of silicon partners that have signed up and signed MOUs. NXP is the first to announce actual tape-out dates and commercial samples for the next Azure Sphere chip that they're going to be producing. We're really excited about that. And you'll continue to see announcements in market for silicon partners that are going to take on the Pluton runtime effectively and meet those minimum security guarantees that we've asked for. And then we'll be working with them to bring all of their drivers and their own and basically Linux kernel over to those chips. So, as Ryan mentioned earlier, really we get into the OS, the defense in depth strategy. We have this curated user environment. We have the OS services to manage connectivity and chip resources, our Linux kernel, and we have the security monitor that protects access to those resources and manages things like ensuring that it's the only thing that can write to flash. I wanted to come back to the Azure Sphere services. And we talked about this measured boot and attestation and what you get as part of that contract. So the services protects your device, your customers, with a certificate-based auth, as well as looking for emerging threats through error reporting. It responds to those threats with automated updates for the OS, and as well as allowing customers to ship their own updates. So then how are we using attestation? Well, when a device first comes online, we have a certificate pinned. We can tell that we're talking to Azure. The device is speaking to Azure, but then Azure doesn't know that it's actually speaking to a Sphere device. So we use these measured boot values that Pluton has generated, and they get signed with the private key from the device, and they get sent up as part of sending its measurements up to the cloud, and then the cloud can then verify that the software that the device booted with are genuine and are trusted. And if those two things are true, then the device receives a certificate, and that certificate can then be presented to any other cloud service, not just Azure. And if you have the certificate chain to verify that certificate, you know effectively that Microsoft has gone through the attestation process with this device, and the device is an Azure Sphere device. Now, we only issue those certificates for a day. And you might wonder why the certificates are only good for 24 hours. Well, that's our attempt to bound the amount of time that a device is going to be able to misbehave without requiring to go back into a test. That boundary could be shrunk or could be widened depending on business need, but we've picked 24 hours as a starting point in terms of looking at the number of certificates we'll have to issue per day when you're dealing with tens or hundreds of millions of devices. If a device has software that isn't trusted, we can actually force it to update. Basically, by not issuing that certificate, we can make sure that the device goes through the software update process, updates to a new version of software that is trusted, and then goes through the attestation process again, and then it receives this device certificate so it can connect. So if you're running your own Apache web server in your house and you want to, you can have these devices, when they present that device certificate to that server, it can prove by verifying that certificate that it has gone through attestation. It is a legitimate Azure Sphere device. So the certificate is really a token saying that Microsoft's attesting to the device's health. So last, somebody mentioned development experience. With Visual Studio, right now we do development with Visual Studio, and this is basically to simplify the development process. You can develop both for the A cores and M cores simultaneously. But we're also doing a lot of active investigation into other products. We know people want to use command line, we're using CMake, as well as Visual Studio Code across Windows and Linux. So, last, we'll just reemphasize this in terms of our desire to be open. We're licensing the Pluton security subsystem royalty-free for use in any chip for anyone who wants to produce one. We're open to innovation in terms of MCU manufacturers, and we're eventually looking to get to the point where we're taking contributions with the Linux kernel, and open to any cloud. So although we think there's a great better together story with Azure IoT, these devices connect to any cloud after they attest to Azure Sphere and then can start to communicate. So that's the deep dive on Pluton. Thank you very much.
So you mentioned earlier that everything can be updated. Does that include the first software that boots the Pluton firmware?
The bootloader. So before Pluton's runtime boots, the bootloader loads, yes, it can be updated as well.
And that can be updated as well. Okay, that's interesting challenge. The other question I had is, what about time? Do you have any kind of authenticated time, real-time time hardware, or do you just get that from the cloud when you?
Oh, we don't have authenticated time.
What's that?
We don't have authenticated time. That's a difficult problem to solve. Thank you.
So on the Cortex-A, are you using Trust Zone? I think you mentioned that on the keynotes.
Yes. Sorry. Yeah, in the past deep dive. So there's a security monitor that runs in Trust Zone on the Cortex-A, and then Linux runs in normal world, and the security monitor runs in secure world. So and all the peripherals, we talked about the core mapper and talked about all those peripherals and resources. The chip actually extends the secure world signal across the chip. So in any bus access, we can tell whether or not that bus access comes from a secure world request or a normal world request, which helps decide, which helps us with access control decisions.
So you maybe don't want to answer, but is it a Trust Zone solution developed by Microsoft, or is it something?
Microsoft. Okay. It's rolled by us. It's mostly focused on update as well as resource access. So it's very, very small. I think it's 160K, Ryan? Yeah, the code size is about 60 kilobytes. So we don't have applications in secure world. We just viewed that was just a threat model we didn't want to tackle. It's just basically a piece of code that runs in supervisor mode in secure world that manages software update, writing to Flash, and a bunch of other pieces of technology there.
So when you have the conflict between openness and securing everything and signing everything, how do I, to what degree am I able to hack the device and keep it secure at the same time? If I want to load my own kernel on a product that I bought, and then still have it go through authenticated boot and all that.
Great question. I think the plan long term is when we look at silicon vendors, as an example, they're going to need to contribute drivers to the Linux kernel. They're going to need to contribute to the BSP that runs in the Pluton runtime and in secure world. And so we're going to have partners writing code. This is part of the thing we're preparing for as part of moving past general availability is the next chips, as an example. We're going to have a lot of partners writing code, and that means they need access to source. They need to be able to build those binaries.
I assume the kernel source would be accessible in any case because of the GPL. But I'm curious about the security model, how that allows me to hack my own device. If I have the kernel source, I rebuild my own kernel, make changes. To what degree can I deploy it? And
right now you can't. You can hack it and compile it, but because we're not going to sign it without going through a security review, then you're not going to be able to deploy it. What I was getting to is as part of the silicon ecosystem partners, we're going to be able to deploy sets of boards and capabilities that allow partners to load kernels onto devices. And as part of that process of building up that infrastructure, I'm going to expect that we're going to want to have a conversation about how to allow other people to do that as well. How do you have boards that you can load untrusted software on without exposing the ecosystem to risk? Something we talk about a lot. It's something we want to do. We're just not there yet. But the fundamental tension is if anyone can load their own kernel onto their home device and we need to sign it, then that puts the platform at risk. So I think separating between development and production is the key thing for us.
Are there any plans to integrate this service with the slightly smarter devices that are not quite on the edge, gateways and aggregators of various sorts?
No public plans. So.
That's a good enough answer.
I'm just curious for this IoT device about the power management. Which level of power management optimization can you reach? I mean, how do you make sure that the Cortex-A or the Cortex-M can reach deep power state
I think
without...
it's a question of retention. I mean, with measured boot, if you're trying to do something like hibernate, then you run into problems with measured boot, which we don't support right now. But in terms of going into deep sleep, there's nothing that prevents the chips to go into a deep sleep mode as long as you're retaining SRAM or caches. And that's something that has been lagged a little bit, I would say, in our development, but it's something that we're looking into and the platform should support. So. Do you want to just try and say it? Applications for side channel attacks? DPA. I actually don't know how much we can talk about. There are some DPA defenses in Pluton. Basically what helps is that all those cryptographic operations are in silicon and gates, but it's not something we talk publicly about what those defenses are right now. It's a great question.
Question myself. We have members like Xilinx who have very powerful FPGA chips, and they have soft ARM cores that can build into the FPGA. Mm-hmm. You had the slide with the silicon partners, and you mentioned that today you have MediaTek, and next year there will be NXP. Is there any way that, for example, Xilinx could use the FPGA to build a prototype platform and let you have an additional development board straight away?
That'd be interesting to talk about. I haven't thought about it very much. It'd be an interesting conversation to have.
Okay.
So
Come at the front, please. I will not throw the mic.
How's the configuration done for the security separation of the whole system between the A and the M? Is that Pluton that's...
Secure World. So Secure World is basically...
In the A, basically. So you boot into the A, and then the A sets up the security throughout the chip?
Well, Pluton runtime sets up part of it, and the Secure World ND sets up part of it. But they're both... They have different capabilities. But for example, pinmuxing is done by the Cortex-A and Secure World. When you're mapping different peripherals, different cores, that's done in Secure World on the Cortex-A.
Okay, thank you.
Yeah. Or setting sticky bits similarly as Cortex-A.
You mentioned measured boot. Does it mean you have a sort of firmware TPM?
What?
Measured boot?
Secure boot? Measured boot.
Yeah.
Attestation, yes.
So did you have some sort of a firmware TPM?
What type of TPM?
Firmware TPM to store the measurement, or
no,
there's another way you
Pluton, use. So Pluton has this digest accumulation register in silicon, and so we can basically feed it measurements and increment the value of that register. So Pluton has some, I would never call it a TPM, but it has some functionality that's similar to a TPM.
Is that implemented in software or some?
The actual attestation is silicon.
So since a lot of the security depends on the cloud service, am I able to use this in an environment where I'm not allowed to connect to the internet? Can I have a private instance of your cloud services? Or?
That's a great question that comes up a lot, not today. But if you don't have one thing I want to clarify is if you don't have a connection to the internet, the device still functions. Sometimes because the way the talks go, if you don't have a connection to the internet, your software still loads, Secure Boot still works, and your device, let's say it's on a core, can still run the dishwasher. If you lose a connection, none of that stops working. It doesn't require a connection to the internet to function. That was really important to us because you can't guarantee connectivity. The only time connectivity is required is if you want to connect to a web server somewhere and send telemetry up, then you have to go attest first. So that's the only connectivity requirement. And then the cloud services are only used for attestation and update. If anything else that you want to run for telemetry, machine learning, or any other engagement you have for your own data, that data doesn't go through Microsoft services unless you're using Azure IoT. It's all
But for instance, if I'm deploying into a government agency that has separation from the internet, but they still want to do updates, would that be possible?
Not right now.
Okay.
Yeah, thank you. Well, I guess we could go through a process to recover the chips. There's field servicing, which is expensive, where you can actually plug into the chip, but there's no offline connection through a proxy or separate stood up server. It's partially protecting the certificate infrastructure. Okay. Great. Thank you for all the questions. I really appreciate it.
Time for lunch.
Time for lunch. Thank you very much.